Good day and welcome back. For this third installment of arc length, curvature, and more, we are finally to the more portion of the discussion. This video, we will introduce kind of the main concept and ideas, and then in our next few videos, we will explore several examples. So to begin, we are going to look at things called the unit tangent, unit normal, and unit binormal vectors. But before diving into those, we're going to start off with what I'm calling a motivating question. What is the unit tangent vector dotted with its derivative? And this isn't something I expect you to look at and just maybe immediately tell me the answer, but instead some computations are really necessary. And these are similar to some computations that we've done in the past, or at least alluded to on multiple occasions. So the observation to make is that the unit tangent vector, as the name suggests, has unit length. And going back to a property of dot products and magnitudes of vectors, we know that t dotted with t, and for convenience, I'm going to drop this of t correspondence just to make the writing a bit more efficient, is equal to the magnitude of t squared. And if the magnitude of t is 1, we just end up with 1. That is, t dotted with t is equal to 1. Now, we don't want to know t dotted with t. We want t dotted with t prime. So somehow we need to introduce a derivative. So we'll go ahead and differentiate both sides with respect to t. The right-hand side is where it works out maybe the most efficiently. We get back 0. And on the left-hand side, we need one of our product rules for differentiation. We take the derivative of the first, dot it with the second, plus the first, dot it with the derivative of the second. And the order that we take a dot product does not matter, so we have 2 t dotted with t prime on the left is equal to 0, which indicates t dotted with t prime is equal to 0. So in terms of the question that was asked, we now have our answer. This indicates to us that t and t prime, if their dot product is 0, those two vectors are going to be orthogonal to each other. This is the key observation that we need. We will take this and we will define what we call the unit normal vector. We will define the unit normal vector to be this vector t prime divided by its magnitude. And note that this is defined in such a way from our above work that t is perpendicular to n, and they both have unit length. Furthermore, we will go ahead and we'll define the unit binormal vector, and we'll call it b, as t crossed with n. And I'm going to just make a little side note here. The order matters. So with a dot product, the order does not matter. With a cross product, it most certainly does. Remember, t cross n would be the opposite of n cross t. The easy way to remember the order is the order that we've developed this. We start with t, we use t to compute n, then it's t crossed n to compute b. And let's make a quick observation. We've noted above that t and n are orthogonal to each other. And remember, if you take the cross product of two vectors, the b here would be orthogonal to both t and n. So in a sense, what we've created is 3 mutually orthogonal vectors. So t, n, and b are all orthogonal to each other. And if we want to think about this graphically, if we pick any point on our space curve C, there are 3 vectors associated to that point. we can draw the unit tangent, and then I'll say the unit normal perpendicular to it. And note with that unit normal, there's really, a whole bunch of possible directions that it could point in. So I don't know with 100% certainty where it will point, but the intuition is that it somehow points inside the curve. And then B, the unit binormal, is the tangent crossed with the normal. So it looks like it should be about here. And note that these vectors are all mutually orthogonal to each other. So in a sense, it's like a little copy of that first octant, which just floats around the curve, the t, the n, the b. For example, if we pick another point on the curve, you have the unit tangent, the unit normal somehow pointing inside that curve. And then it's maybe kind of tough to draw this, but let's put the unit binormal here. So starting off with a space curve, we can now compute 3 unit vectors associated with it. The unit tangent, the unit normal, the unit binormal. Furthermore, there are several associated planes of interest that are going to arise as well. So let me draw a picture and then we'll indicate a few bits of terminology. So at a point on the curve, I'm going to just kind of recreate what we have above. So there might be a unit tangent, unit normal, unit binormal. And in this definition, we say at a point P, so we have our point P where we found that unit tangent, normal, binormal, the plane determined by N and B. That is to say, and I'll shade this in green, the normal and the binormal vector at that point P, they determine a plane. And note, as you go around the curve, that plane is going to change, but relative to a specific point, you have this plane. And that is referred to as the normal plane to the curve at P. And an observation that I would like to make to go along with this is this normal plane is defined by a point and a vector normal to the plane. The point you have is the point P, we've already discussed, but we can very clearly see from our picture to the left that the unit tangent vector is perpendicular to this normal plane. So the normal vector for the plane would be given by the unit tangent vector. And that's the unit tangent vector at the point P. Furthermore, there are several other planes, but the other one of key interest is the one determined by the unit tangent and the unit normal. We refer to this as being the oscillating plane to the curve at the point P. So let's go ahead and indicate that in here in red. So there's this plane which is determined by N and T. We refer to this plane as the oscillating plane, whereas previously in green, this was referred to as the normal plane. And once again, if you want to write down the equation of a plane, you need those 2 key ingredients. A point on the plane, which it's a plane going through P, and a vector orthogonal or perpendicular to the plane. And for the oscillating plane, we can very clearly see that this binormal vector is orthogonal to it. So the normal vector for the oscillating plane would be the binormal vector. And note that's the binormal vector at the point P. So with that observation in mind, I do want to note, if you are asked to find the oscillating plane for a space curve at a point, that is a somewhat, maybe I'll even say devious question, in the sense that it requires you to do quite a few computations. You have to go through and determine what's the unit tangent, then the normal, then the binormal, because that binormal is going to give you the direction normal to that plane. And this completes our discussion of the material and the terminology. what remains in our next two videos will be going through examples and getting practice working with these quantities. So stay tuned and take care.